Permanent magnets are difficult things to understand. In fact, if we're absolutely honest with ourselves, we don't understand them. You see, either end of a bar magnet will attract a piece of steel. But it doesn't follow that because it's painted red, it's a magnet. Because look, it won't pick up that piece of steel, but this one will. So this one's the magnet. But the only real test between two magnets is whether or not, in addition to attracting each other, they will also repel when reversed. Now, the idea of repulsion gives you the impression that perhaps you could float one of the magnets over the other, like this. Now, I can feel the repulsion. Now, watch what happens when I let go. You see, it won't stay there. You get the repulsive force, but we say it's not stable. Now, people have proposed this idea for suspending railway carriages over a track because it uses no power. But then you have to do something about stopping it falling off sideways. Now, we can make ring magnets like these. In this case, the whole of one side is a north pole and the whole of the other is a south. So if we get two of them, we can try and float one over the other. And again, you see, you get the lift, but we can't get the stability unless we put in a glass tube. And you get floating. Oh, isn't that just marvelous? People have suggested you could use this for floating railway carriages, but you see, the clearance there perhaps isn't big enough. So what we'd really like to have is some more magnets to make it stronger. That's going in roughly the right direction. Now we're getting a lot of clearance. But of course, these magnets would be on the track and this would be the vehicle. So this is going to be very expensive. You want hundreds of miles of this. So what we'd really like to do would be to put a single magnet on the track and have more magnets on the vehicle. 2 magnets, 3 magnets. The gap, instead of getting bigger now, is getting smaller. So this is a situation which gets worse as it gets bigger. So it is no good for railway vehicles. Now there's another kind of magnet which doesn't involve the use of rings or anything like that. Instead, a coil of wire. We're going to take an iron bar and push it through the center of the coil and then pass an electric current through the coil. Thank you, Barry. This meter will tell you how much current is passing. You connect that one, Barry. I'll connect this, or you connect the switch. All right. Now all we need is a battery to connect to here, and we shall be able to make a magnet out of that bar of steel, which at the moment is not magnetized. Now if you give me the board, Barry, we shall be able to see whether it behaves truly in the manner of a magnet, because here is a magnet. At the moment, this is just a bar of iron, so the magnet will attract either end. Now let's see if we can make it repel by switching on. Get current. That end will now attract, and that end repel. So now we've made an electromagnet. But will it work without the iron core? We'll just use the coil alone. Well, it certainly attracts. And I turn it round, and it just repels. So it is still a magnet, even though it has no iron in it at all. But of course, if we put the iron core back, then the attraction and repulsion is far greater, so we make a better magnet. Now let's see how much weight we can lift with this magnet. Barry, pass me the iron bar. I'll see if I can pick up this heavy iron bar. And we can, just. It's not actually jumping up to meet it, but having made contact, I can just lift it. But there's more magic in an electromagnet if, instead of feeding it from a battery, we feed it from alternating current. Look at this oscilloscope. You see a spot rising and falling. That spot is really measuring the amount of current that flows in a wire. When it's above the middle line, the current flows one way, and when it's below, it flows another. Now, I've slowed this down to show you what is really happening, but in your house, you have an electricity supply which goes much faster up and down, even than that. Faster even than that. It goes up and down 50 times a second. Now let's have a look at an electromagnet over here that uses that kind of supply. And this is a coil of wire with a long iron core. This is a ring of aluminium. Aluminium, you know, is a non-magnetic substance. We can't pick it up with a bar magnet, as you can, for example, a bunch of keys. So we'll put this non-magnetic ring over this iron core and switch on. You see that? You get the ring thrown high into the air. If, without switching off, I put it back, then it floats. But notice it never floats level and in the center. It always has to lean on the pillar, just like the permanent magnets did. If I put a thinner ring on, it doesn't float quite so high. Thinner still, a lot lower down. And if we go to the ultimate and cut a ring from kitchen foil, which is also aluminium, that doesn't float at all. But unlike our permanent magnets, if we now add some more rings, we shall begin to see the whole lot lift. Remember, with the permanent magnets, the more magnets we put on the top and the smaller was the lift. And in this case, the more the rings, the higher the lift. Put the thicker one on, thicker still, and up it comes right to the top. Now, what is the secret of this amazing device? This is the giveaway. This is a copper cylinder that is free to spin. If I hold the copper cylinder alongside, there's nothing much going on. But if I take this ring, which wants to float up there, and I force it down alongside the copper, then the copper begins to spin. And if I put it on the other side, it spins the other way. It is as if there was an upward sweeping something which is causing the copper to spin. And we call that upward sweeping something a travelling magnetic field. Now, this is a row of electromagnets arranged deliberately to produce one of these travelling magnetic fields. So when I switch it on, put our copper cylinder over it, and there you see the same effect, as if something was sweeping underneath it. When we put a bit of aluminium on, it does push it along, but not very fast. Let's try a bigger piece. That's better. Bigger still. Better still. You see, the bigger you go, and the better it gets. This, of course, we call a linear motor. Now, suppose we increase the current. Would you mind increasing the current, Barry? And we can now hold a sheet of aluminium which is not only trying to be pushed along, but it's also lifting above the surface. It's much more like what you would expect if you threw a piece of wood into a flowing river. It would float and move along. So this then is the beginnings of a magnetic river. But it hasn't got any banks, because if I take my thumb away from here, it'll fall off the side. If I take it too far towards you, it'll fall off the other side. But if only we could stabilize it, then we should have something that looked exactly like a river. Now, how does all this work? Could I have the row of rods, please, Ray? This is a mechanical model of what you've just seen. Instead of a row of coils, we've got a row of rods. We're going to feed them with alternating current so that each one can rise and fall. And when we turn the whole thing, we get the impression of something travelling along. But I want you to notice that nothing actually travels along, because each rod only moves up and down. The thing that makes it real is when we put something into one of the troughs of the wave. Then something real travels along. You can make it go the other way. If you watch an individual rod, such as this one, you'll see that it's only going up and down. There is no horizontal movement at all. Only the ball is a real thing moving side to side. It's exactly the same with this magnetic river. I can switch it on, and there is nothing above there, nothing moving horizontally, until I put in the aluminium, and it's like putting the ball into the rods. So this is our first step towards a magnetic river. This is a single coil and a plain sheet of aluminium. So it will behave rather like our jumping ring. Switch on and up it goes. Try and put it back. It floats. It has a really good try at floating, but it doesn't make it. But if we place it not in the middle of the coil, say it like that, then it doesn't jump straight up. I put it to this side. I put it towards me, and so on. Let us use this spinning cylinder again to see what's going on. Switch on, put the cylinder in the center, nothing happens. Introduce the plate, and it spins. Introduce the plate from the other side, spins the other way. Notice which way. It's trying to throw the plate out. So to try to do this is like trying to balance a pencil on its point. You just won't succeed. But this idea of producing travelling fields, like this, has given us an idea. If we could only produce inward travelling fields without the plate there, then we might have a chance of holding the plate in the middle. So let's try and do that. Instead of a single coil, I'm going to use two coils, one inside the other. This is a coil, and this is a coil, and these three rings are steel rings. They're to help to strengthen the magnetic field. Now, we've found that we can produce this inward travelling field if we make the current in this coil go that way around at the same time as the current in this one is going the other way around. So when we put both coils on together, we can perhaps detect with the copper cylinder a very slight tendency to produce inward travelling fields. That is the bottom of the cylinder moving towards the centre. That's what we're looking for. Now, magnetic field takes no notice of pieces of wood or cardboard or paper, so I can pass a piece of wood underneath without affecting the floating disc in any way. Now, I want you to imagine that we've been able to take this solid structure, put it under a steamroller, and roll it out flat, really flatten it in this direction. And let's try and imagine what that would look like. Well, here's our aluminium plate, and we'll switch it on. Now, there is our aluminium suspended, but not yet movable. I can push it by hand. It's as if we had a magnetic river without any flow. It's quite stable, but it needs something to push it. So just to demonstrate that, I'm going to put a little air screw on it. And when I switch this on, you get your propulsion. There was a time when we thought we should have to put a linear motor up the center between the coils to get propulsion as well as lift and guidance. But a few months later, we discovered that all that was necessary was to break up these two coils into a set of smaller coils, and we could get the lift, propulsion, and guidance from one and the same set of coils. Now, here is one row of coils and the other one at the other side. But this time, the coils have been divided up into groups so that we can produce a traveling field as well as give lift and guidance. The thing we're going to propel in the magnetic river is this sheet of aluminium, and we've stuck some tape onto it so that you can see it more easily because it goes rather quickly. So, Barry, if you'll take this, please, and put it on the end and switch on, we'll have a demonstration. Now, I'm going to change over two of the connections to this end of the track so as to make it fire backwards. Now let's see what happens to our aluminium plate. Switch on, Ray. Now, this back-to-back motion, of course, has got nothing to do with passenger-carrying vehicles. It's more suitable for propelling shuttles in weaving looms. So I'm going to change back the connections because I'd like to show you the train. Now we're going to dress up this piece of aluminium to look like a passenger-carrying vehicle. The scale of this operation is such that this will now travel at the equivalent full-scale speed of 250 miles an hour. And Barry, if you'll start this one, I'll have to go and catch it because this is rather expensive. Now, it's possible that we shall see this kind of vehicle carrying passengers.